Okay, so back to sharing the screen. This is this guy here, as we're talking about. It's got lots of features in it. The most likely button you're going to be pressing a lot is this one here. And you're going to be using edit to put your data in, and then this one here, calc, to get all your answers back. But that's only the beginning of things. We're going to use this calculator also in different chapters to do linear regression. And we'll also use it to do z-scores, normal distributions, hypothesis tests with p-values, you name it, pretty much it's going to get used a lot. So get a TI-84 physical or download this and it'll do the job for you. So that's all I kind of want to say about this one for the time being. And stop sharing that screen. And I'll start sharing this one. So I'm going to use this as our first example of today. There's a question here, I mean, they're quite long-winded, but essentially it's using a property, the empirical rule property, I believe it's called. It has other names. Shows you, I got the name way back at university, and so when they give something a name in university, sometimes they give it a bigger name. So if you want to impress people, it's called the empirical rule, yes, the empirical rule of statistical regularity. And I didn't make that term up. It basically tells us how we can work with data. And if you have enough data and it's roughly symmetrical in shape, and this guy here is the mean. Let's suppose that the mean is 100. And I'm going to use that notation, X bar, to represent the mean of the data. And you've got the standard deviation, SD, and I'm going to pretend that it's 10. Although on your calculator it's called SX, but it's the same thing, right? So let's suppose I've got some data where the mean is 100 and the standard deviation is 10. Actually, IQs look like that. So I know they're out of fashion, but there used to be a time when IQs were much more popular as a way of predicting people's intelligence, although that's not, strictly speaking, what it did measure. So what the empirical rule says is that if you go one standard deviation either side of the mean, in this case, if you go from 90 to 100, right, that's add 10, take away 10. Inside this region, between 90 and 100, they have found from experience that 68% of all the numbers, all the data is in that range. It's quite an interesting fact. It doesn't matter what the mean is. It doesn't matter what size the standard deviation is. But if you take the mean and you add the standard deviation, you take it away, in that chunk of space, 6 to 8% of the data lies. In IQs, that means if you took the IQs of everybody, say in America, which is basically an IQ of 100 as we have here, 6 to 8% of the population, a little bit like 2/3 of you, would be in the range of 90 to 110. Now, if you go two standard deviations, so I'm going to write that down as X plus or minus a standard deviation. That gives you 6 to 8% of everybody who took part. If you do a mean plus 2 standard deviations, so in this story, you would start at 100 and do 2 of them, that would take you to 120. And if you took 2 away, that would take you to 80. And in that range, 95% of all the data lives. So 95% of Americans will have an IQ somewhere in the range of maybe as low as 80, maybe as high as 120. And so in that range, you'd have 95% of all the people. And then depends on the textbook. Does this textbook, because I haven't looked at what the homework says, does it go to 3 or does it just say after that it's almost everybody? Does it do 1, 2, and then 3? Anybody?
No, it doesn't do a third one. It just does 1 and 2.
Right. If you look at other textbooks, because you're going to look online, you're going to see different versions. There's another one that adds 3 standard deviations. And if you want to do the mean add 3 standard deviations and the mean take away 3 standard deviations, then the answer is almost everybody, or more precisely 99.7% of all data. Now, why is this empirical rule so useful? If you collect medical data on anything, right, and I'm not a medical person, so I'm making this up, but let's suppose that potassium levels in your blood was an interesting thing to keep an eye on. Right? So, since I'm making this up, I'll just put in my own numbers. But let's suppose that for a typical adult, the potassium level is 70 units. So that would be the mean. And let's suppose that the standard deviation for potassium was 5. When you get your blood work done, if you do as I do, because of various issues I have, when you get your blood work done, you'll normally find that you're in the normal range, that you're in the extra high range, right? Or you're in the lower range, right? And so you sometimes get little warning signals that your doctor would say, yeah, your blood pressure's a bit in the high side, or your potassium is a bit in the low. If you look at that, 1 standard deviation takes you to 75 and 2 takes you to 80. And take away 1 standard deviation and take away another one. If I was looking at this picture here, that boundary at 80 might be the one that gets flagged. So they take your blood and they look at your potassium and they give you a number, and then next to it they say high. Right, you ever seen that kind of situation in any of the things? Leanne, I know you're a nurse. Do you get data that basically anything to do with that would indicate this is too high, or in this case, if you had the number over here, it would be considered on the low side? Don't know if you can hear me, Leanne. Yeah. Do you want to throw in any comments on what I just said? No, okay. She agrees with me then. So
I think you are spot on. You're spot on with that.
Okay, so if you wondered where did they get the numbers, now you can do it for anything. Do you know you can do it for babies and their weight? Right, there's a typical average weight for a healthy baby, and then you get little fat ones and not so fat ones, and they have a kind of cut-off number, and they say, especially on the low side, they get kind of worried because on that side, there's severe health issues. So they weigh a baby. Pretty much one of the first things they'll do is weigh a baby, just as an indication of what's going on. And they keep an eye on the weight of a baby for quite a few reasons, but one is obviously the health. So you need to know what is a healthy weight for a new baby, and you can even reduce that to only premature babies, and then do the average weight of premature babies and what their standard deviation is, and therefore you can come up with all these kind of interesting cut-off points that make it worthwhile for you to say, okay, this baby's weight is not good. Maybe we have to look into something that might be a problem, a health issue. Right. So, now this is one that I'm going to look at just to get it out of the way. Well, not to get it out of the way, but because it causes issues. It's a big, long question. Jamie, I've lost the number. Do you know what number this was?
3.2.29.
Oh, it's up the top, right. So it's quite near the end of section 3.2, and it gives you one of these stories involving some data that you'll get in the next picture, but it says the empirical rule, right?
Yes.
So the empirical rule of statistical regularity, that guy, and 68% is 1, 95 is 2, that's fine. So if you were being asked then what percentage you would get, and 68% would be within 1 standard deviation. And then I think the question got down here gets a little bit out here. It says, estimate the number that fall in the interval between 1 standard deviation above and below the mean. And the picture that they have along with it is this guy here. So it's not a great copy, but I'll try and emphasize it a little bit. There's the mean in the middle. This guy and this guy are the add one standard deviation, and this is what you get when you take away one standard deviation. And the numbers are pointing roughly between here, from what I can see, here. And the correct answer out of the 4 choices was A. So I'm going to write down what A is so we can see it with a picture. It's 21, add 34, add 27, and finally add 2. And you're saying, well, how many people did that represent and where did those numbers come from? Well, when I look at this picture, do you see that that rectangle is totally inside this range?
Yeah.
And that rectangle is him. And this one next door to it is totally inside the range, and that's him. Now, what is less obvious is, do you see this line here bites a little bit of this rectangle? And they're saying it's 2. And this bit over here bites into this 32. It's not all of the 32. They're saying it's 21.
So sorry.
Yeah.
So the estimated value is 21 and 2. So they just like estimated.
Yeah, they just did their best guess. Now you say, well, I find it hard to guess that that little sliver is worth 2 people and this bigger bit is worth 21. But the question is, it doesn't really matter when you look at the choices, because that one is wrong because it doesn't have anything either side. It only has the 2 main rectangles. This one, I believe, is wrong because it's using all of those 2 rectangles, and it's not all of them, it's just little bits of them. This one is wrong because I don't even know where they got the numbers from, but it's wrong. So by a kind of process of elimination, you get that one.
Okay.
Okay. And then I think that would be the end of that particular question. Yes?
I still have questions there, sir. Regarding the 120, why they did divide it to 120?
Oh, the reason they divided it by 120 should be somewhere up the top here, because that was the total number of people that were in the survey.
Oh, the number of the people on the survey.
So I can't remember where it says it, but somewhere in the details you'll come across it and it talks about it.
Okay.
Okay. Right. So have we got someone else with another question? And I will help you with it, or if not, we'll just talk. If you've got a topic that you want me to go over, that works too.
I have one, but I have to find it on Pearson real fast. Just give me
Okay, you go do that. Sure, that'll work fine. I know Arlita just came in a few moments ago, but the other person that just came in, I forgot to write your name down. So if you could chuck in your name so I can write it in my kind of class register. Who were you? You just arrived a few seconds ago.
Professor Robertson?
Yes.
This is being recorded, right? So I could watch it later?
Yes.
Okay, because I have to go. I got called into work. Somebody called in sick.
Okay, well, thanks for dropping in, and hopefully you can catch up on this later.
Yeah, I'll be able to. I just wanted to make sure that I could come back and watch it later.
You will. That's my plan.
Okay.
It's not 100%. I've had issues with Zoom. When I leave this, it automatically saves it, and then things happen.
Okay.
I go and look at it, and it's got no sound on it or something weird. But
Okay.
I'm not expecting it. I'm just saying it might happen.
Okay. If I have any questions, I'll email you.
That'll work. That's perfect.
Okay. Thank you so much.
Not a problem. Okay, so the person who was saying they're a way to find the question, have you managed to find it now?
My computer's been super slow. I'm almost there.
Okay. Is there any, while that's happening, is there any general questions? Are you all happy about this empirical rule where you take the mean and you add one standard deviation, take away, and then add and take away 2? And one gives you 68 and the other gives you 95, and you can use those types of calculations. You all comfortable with that concept? Okay.
Sir, I have a general question.
Sure.
regarding the result for the test one, because I tried to look on the MyLab and it's not showing the score, and I tried to review the test one, but it won't let me. It says
we talking a quiz or a homework question here?
the test one, sir, the one that we did last week.
Oh yeah, test one is over. So the reason you can't see it is it's probably closed. And if they were trying to get into it, is that what you were doing?
Nah, yeah, because I'm trying to review it, because normally I can see the review on homework, quizzes, and stuff, but the test one, I can see the review and the score is not showing. I don't know if I'm only the one who
I
experienced.
doubt it. You know, whatever you see, pretty much everybody. So I'm going to just take a note to myself to see if there's somewhere I can go in and look and see what's going on there. Your test score was adjusted according to the homework, not the homework, according to the working that was sent in. So some of your scores are bigger than what the computer says, because I found it easier just to take their number, add on yours, and I've put it on a separate spreadsheet that I've got. So even if you did see your score, it might not match your real score. Your real score is always going to be at least that or better. It's never worse. Okay, are we ready for that question?
Yeah. So
Okay.
the formula in 3.3 with the, I think it's the Greek letter over the square or under the square root. Could you use that in an example so I could get a
Okay,
better grip on it?
let's see. You have a formula with a Greek letter over a square root. Do you have a question number for that, and I can go in and look for it?
There's not really a question number. I know it's on page 100 of the textbook.
Oh, the textbook.
Yeah.
It sounds like you're doing the theory. Okay, so there's a Greek letter. Does it look like sigma? Oh,
It's like an E. I don't really recall.
okay, I think I know what it is. I got you. I'll show you.
Thank you.
You probably see this fella.
It's close to that, but it's a little more complicated. It has the n-1.
Oh, okay. You are looking at the formula for the standard deviation.
Yes.
Well, there are two versions of it. It's the same one.
Yep, that's it.
I'll go that way, but there is the other way. Right. That formula is only for theory. You do not need to know that. That's the formula that you would have to use if you wanted to calculate the standard deviation from a set of data. It is horrendously number intensive. What we do instead is we get our calculator to do it for us. So if you look at the video that we have on Canvas, it'll show you how you can find the standard deviation by just putting the numbers into the calculator and going to a special menu that they've got in one variable statistics, and it'll tell you what the thing's called.
All right, sounds good. Thank you for that.
Sorry about that. I'm using my phone as the second camera, and of course that means people can phone you. So yeah, that's all I want to do. I want to get into details that aren't necessary for you. It's the theory behind how they calculated it, but when you see how they calculated it, you probably would never do it by hand. In fact, no statistician I know ever calculates standard deviation by hand. We all do calculators instead.
Heard that.
Okay, so we got another question? If not, I'll just randomly.
I actually do have another question.
Oh, cool. What you got?
So for the test one, I didn't turn in any answers because I didn't really need to write anything down.
Yeah, that can happen, in which case your test score is just going to be the same score that the computer gave you.
All right, cool. I just wanted to make sure if I need to turn anything to Canvas or not.
No. Some homework questions, you know, it's A, B, C, and D, and you pick C, so there's not really much you could do about showing me working for something like that. And I understand that some questions in some chapters that you're going to do will have a lot more working to them, so there will be more to send me. But yeah, you're right. I didn't see an awful lot of situations where there was much working, so it doesn't surprise me.
Sounds good. Thank you.
Okay, now I'm in the assignments page. I don't know if you can see that, so I'm going to have to go into a share. And where are you now? I had it signed ago. Here, there we go. Right, this is section 3.4. So if you don't have any particular problem, I'm just going to pick one of these and see what it looks like. So 7's my lucky number. Let's see what it looks like. So just give you a feel for how these questions work. Right, so the accompanying histogram shows the number of pairs of shoes reported for 322 males and 300 females. So what you are looking at here is basically a summary of all that information. So before I even look at this, let me look at some of the data and see what I see from it. Well, the typical, if you use the mean, the typical number of pairs of shoes for women are 28 and for men it's 11. So we can be nice and sexist here. I can guarantee this is true for my wife. She has at least twice, if not 3 times, the number of shoes I've got. So this, when people say, you know, evidence-based, what they're saying here is, I have some evidence to back up my statement. It's not anecdotal, you know, like, well, my wife buys a lot of shoes, so that's evidence that every woman buys more shoes than men. That wouldn't really be evidence. But what we have here is a large sample, and on average, women have 28 pair, on average, men have 11. That's kind of interesting.
Professor, not to
Yes.
interrupt, but we're only seeing the question numbers. We're not actually seeing the question at the moment.
Oh, thank you for interrupting.
No
The
problem.
sharing mechanism on this is whenever, at least I have to do it, there must be a better way of doing it. I have to go out and back in. There we go. There, you should see it now. But mention that to me through today or any time if this happens, because I think it's important. So there's the 28 and the 11, well, roughly 12. Now, if you use the median instead, you see that that relationship is still holding true. And it's very often useful to know the mean and the median. I'll give you an example. Can you imagine I had a set of data and the median wealth of people in Washington state was $30,000. So that means if you sold everything that you owned, right? The clothes on your back, your car, right? Your children, you sold everything you owned and you paid off all your debt, that on average you'd have $30,000 left, right? So you can imagine selling your house if you had a house and paying off your credit cards. Now the mean is 30,000. Right? If I calculated the median, do you know it might only be 10,000? Both of those are measuring a typical person's wealth in Washington state. The problem is that the difference between them is huge. And when the difference is huge between a mean and a median, what that is telling me is there's at least a good possibility that there's some outliers out there. Because the mean gets affected by a few really big numbers. Take the Washington state thing. Do you know why we all have so much more money when you do the mean? Bill Gates. Bill Gates is worth billions, right? Can you imagine his wealth being averaged out with everyone else? Can you see how that number would move the mean well to the right? So knowing the mean and the median is useful because it tells you whether or not there is a likelihood of outliers. If they're both the same, and I'm saying this guy is 28, right, and this guy here, the equivalent in the women is 22, although they are different, they're not fantastically different. It's not like one's twice as big as the other, but there is a discrepancy. What else do I know about this? Well, if I look at a different figure, and we look at, let's look at how spread out the data is. The females have a standard deviation of about 22, and the males have a standard deviation of 12. That means not only do the males typically have fewer shoes than the females, but they tend to be pretty consistent. There's not an awful lot of variation, at least within the men. Within the women, isn't the number almost twice as much? So I'm looking at, if you imagine two pictures, can imagine one of them is really wide and lasts for a long time. It kind of goes like this. So the guys would be like this, quite tight, and the women would be, whoa, forever. So you can pick up all sorts of cute things for this. So let's click on this icon to view the histogram. Now, when I look at this one, do you see that for the males, almost all of the information is pretty close to each other? And then it kind of drifts off. Now you look at the women, do you see that there's a lot more data, even at the end? Let's add some other questions to this. If you look at this data, I see a skew to the right. Do you see a skew to the right? It goes up, and then the tails off for a long time. If I look at the women, it goes up and it goes down. I know there's some annoying little bumps in the way, especially this one at the end, but skewed to the right doesn't mean perfect. It just means that's its basic shape. So both of these are skewed to the right. If I was figuring out where the average woman is, do you see it's much higher? My guesstimate would be around about here for the males. Now the histogram for the men's distribution is strongly left skewed, strongly right skewed, or roughly symmetric. Well, I already answered that one, didn't I? So I would pick the right one. Now let's see about the women. I would also go right skewed. So if that was a test question, I don't think I'd see any working for it, right? What working could you give me? It's a visual thing. Well, that was a kind of random question. Never quite, it's frozen. Oh, it came back. We're good. I'm always worried when I'm on these that something's going to suddenly crash on us. Okay. So, have any of you seen or looked at what's called box plots? Right. So, not everyone has. So, let me show you what a box plot looks like, and I'll show you how you can use a box plot to decide whether data is roughly symmetric, skewed to the left or skewed to the right. It's easier when you see a histogram and it's drawn for you, and it should be easy for a box plot as well. So it's made up of what's called a 5-figure summary. The median has also got another name, it's called Q2. And this is called a 5-figure summary for obvious reasons. So let's suppose that's 1, that's 3, that's 10, that's 20. No, let me change that. That's 17, that's better. And that's 26. Okay. So you imagine drawing a ruler and starting at 0 and going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, somewhere like that. Then the minimum score was 1, so you put a little mark there at 1. Then you go to 3 and you do a bigger rectangle. Then you go to 10, you do another one. And then you go to 17. You do your third big one. And then you finish at 26, which would be about here. You do a little one. These guys get joined together like that. And these two fellas get joined together like that. And this is called a box plot. And you see, basically, you just have 1, 2, 3, 4, 5 numbers, and that's how they created it. So if you've seen a box plot and you wonder, how did those numbers generate that picture? That's how you do it. So let's imagine that you've created a box plot. And I won't do all the details, because I want to do a relatively quick version. If the picture looks like that, then we would say the data is symmetric. What that's telling me is, do you see these two sides are pretty much the same size? And these little guys here, called the tails, they are also pretty much the same size. So if you ever see a box plot that looks like, you know, even this way, boxes even, line in the middle the same, you're looking at a symmetric set of data, typically. Here's a different box plot. Right. Don't need the numbers to answer this question. What shape is that? Is it symmetric, skewed left, skewed right?
Skewed
Skewed
left.
left.
Right. What tells you? You have two of you in the same time. What tells you? What do you look for there that says, yep, skewed left?
There just seems to be more information on the right.
You mean the left? Or
Yeah.
do you, I don't know what you mean.
It's spread on the left.
Yeah. You see this bit here? A lot of big box on the left, a lot of tail on the left. On this side, a little squeezed in box, a little squeezed in tail. That's what skewed left looks like. Now for symmetry purposes, that's what a skewed right would look like. When you look at the boxes, do you see the boxes more, there's more of the box on the right than there is on the left? And when you look at the size of the tail, isn't there more of a bigger tail on the right than there is on the left? And that's what skewed right looks like. So if they're evenly balanced, symmetric, if box and tail are big, it's on the left. If box and tail are big, it's on the right. Left's good, right's good. So what would this one be?
Tricky.
Tricky, because
Seems tricky.
it's a trick question. It's none.
Right.
It has no particular shape. Do you know sometimes you get a histogram and the boxes are just up and down like everywhere? You can't tell any discernible pattern. Because a lot of data doesn't have patterns, right? It's just random numbers that don't really have any going up and then goes back down again. It kind of, they just zoom up and down all over the place. So this shape here has none.
But it looks like it's skewed to the left.
Okay, well, oh, because of the box?
Yeah.
Right, which it is. But what about the tail? Isn't the tail saying it's skewed to the right?
Yeah.
And you can't be skewed to the left and skewed to the right. You can't be both at the same time.
Mm-hmm.
Now, whenever you do a box plot, there are going to be two tails, right? And they're going to be a box cut into pieces. But if they don't match in both pushing left or both pushing right, if they're kind of counteracting each other, which is what that is doing, then you're basically looking at no shape to the data, right? There's no shape, at least a skewed left, skewed right, or symmetric, we'd call it. Who knows what it might look like, but it doesn't have a name, whatever it looks like. Are we good? Right. Is there a concept that, yes? Is there
I
a
have a
concept?
question that's
Yeah.
not related to this. I
Fine.
was wondering how we would be able to see our test score for the first test and how we could review it, if possible.
The review part has been brought up by Jamie. I'm going to go and look into what I can do about that. Your test score, did I not send you an email? Tell me I did, because I believe I did, which gave you your grade with in it. You got your test 1 score.
Yes, I received an email.
Right. So,
Yeah, me too.
Right. So that's your test score. So that's
Very
what you
nice.
got.
Thank you.
So if I may have get caught in the
Yeah,
Yeah.
so It will not show on the MyLab.
Well, it won't. I don't know how that's going to work. I think once I close, the way it works is I tell it it's finished, and I think, I don't know yet because I haven't looked, but I think it closes the thing off and that's it. And I'm going to think of going back in and seeing if I can open it. But I have to be careful that I don't open it and then it becomes doable again, because then that might really screw up. So I want to be really careful that I only open it up as a you can see it but you can't touch it kind of version.
Yeah, so
and that's going to make, I have to be careful about that. So if you're wondering what questions did you get correct and which questions did you get wrong, are you more interested in knowing that?
yeah.
Yeah, I think I can print out the individual scores that each question got you. I think I can do that. I sort of remembering a menu that I was in once that allowed me to do that. So I will write that down, see if I can print. If I can, I will do it. If I can't, then I guess I can. Right, we've got to, oh, darn it. Somebody came in late and I didn't know how long they were there for. I apologize to the person who just arrived. We were doing all sorts of things and I didn't notice that I had more attendees. Right, we've got probably time for one last topic. I've picked, in this case, box plots, and I've also done the empirical. Do you want me to show you how to use the calculator to get standard deviation and things like that? Would that be a worthwhile of your time?
Yeah, sure.
Okay. Right, let's me see if we can do this then.
Oh, also, I appreciate how much time you gave us on test. That helped out a lot.
Yeah, the test is yeah. That's fine. I have no problems with giving you time. I want to make sure you can at least show what you know.
Yeah, I was able to revise and that helped out.
Okay, here goes. So you've got your calculator, it looks like this. Let's suppose I want to do one of those 5-figure summaries, right? Because I wanted to draw a box plot from scratch. So I would go stats and I take number 1, which is edit. Now the chances are if you've done more than one question, you'll have data from, question 8 still in the machine. So that cursor is over 98. There are other ways to do it, but this one works pretty well. Just keep, can't even say the word today, keep hitting delete until they go away. And then let's put in the numbers. It's 1, 3, 5. Oh, I've got a better idea. Let's collect data from those who want to share. So I'm going to collect data, and as I hear it, I'll start typing it in. So there might be a little bit of 2 of you say it at once, and that's fine. I'll figure it out. And you're going to tell me how many siblings you've got. So how many brothers and sisters that you have, including yourself. So the answer is obviously, if I'm an only child, it's 1, right? And only those who want to share need to join in here. So I'm going to share because I'm one of 10 children. So who wants to join in with theirs?
I got 3.
Okay, so you're in a family of 3.
I got 5.
Any other volunteer?
I'm the only child.
Okay, go for it. Somebody say it quick.
3.
Okay, another 3.
5.
Another 5.
2.
Okay, a couple more should do. If we have 2 more volunteers. I'll put in my wife's family, who is 7. And any more? One more?
have 3.
3, okay. Now, so you got your data in, that's great. And this represents numberless siblings in your family. What we want to do now is, if you look at the video, I tell you how to change things if you make a mistake and so on, but we'll assume it's perfect here. So you hit start again, you go over to number, the calc one, and you choose one variable starts. As long as that cell one, leave it alone. You hit enter a few times. And for our class, the mean number is 4.75 and the standard deviation is about 2.66. And if I move my little cursor down, we can get the 5-figure summary. And it's got a minimum of 2. The Q1 is 3. The median was 4. The Q3 was 6. And the maximum was 10.
Quick question. What does the Q1, like the Q stand for?
Q stands for quartile 1. So if you imagine, well, let me go back to the data and I can maybe visually show you what that looks like. Okay. So can you imagine you had a whole set of data, not just ours, but a lot of data, right? Hundreds and hundreds of people. So what you do is you queue them up from the smallest number here to whatever it is, the biggest number here, right? Now, if there was, roughly, say, 100 people, to get the median, you walk to the middle person, and there'll be 2 of them there, and you say, how many kids in your family? And they say, 5. That's Q2. That's the median. Now, what has happened is that I've now split my data into 2 groups of 50, right? The 50 with lots of kids in their family and the 50 with not so many kids in their family. Now, if you do this group and you imagine walking along to the person in the middle and they say, right, roughly position 25, but there's really 2 numbers there. How many kids in your family? And you say, there's 2. Well, that's the guy we call Q1, the first quartile. It's the middle of the first half of data. And if you do the same over here, you get somebody and say, how many in your family? And they say 8, that's going to be called Q3. So if you imagine your entire 100 numbers, it's really been split into 4 distinct groups. The first 25%, the second 25, the third 25, and then the last 25. Do you notice that there are 4 groups? That's why it's called quartiles, which might seem a bit strange because there's only Q3, Q2, and Q1, but they separate it into 3. So that's what you're finding when you find Q1 and Q2.
Thank you, that helped out a lot.
Right, so let's go and make a 5-figure thingy bob of this fella. So we'll start at 1, then there's 2, then there's 3, 4, 5, all the way up to my guy. And you start with a minimum at, what was the minimum? We had 2. So you do a little mark at 2. And then you go and you do the median, which is at 4. Q1, which is at 3. Q3, which is 6. And finally, 10. And then you join the boxes together. And you go like this, and you go like that. That box plot is a kind of visual summary of the data I just collected. Now, it's a little bit artificial because I only collected a few numbers, but can you imagine I collected thousands upon thousands of numbers? You would end up with similar looking result, right? Now, when I look at that picture, skewed left, skewed right, or roughly symmetric?
Skewed right.
Skewed right. Now, do you notice that the tail is bigger on the right and the box is split bigger on the right? Right? When they both agree, skewed right. So we can look at that and we can say, and I wouldn't because it's such a horrible small sample. Oh, do you know that the number of children in your family, the distribution is skewed to the right? And if I think about it, it kind of makes sense. I'm pretty sure it's real. If you look at a normal's a bad word. If you look at a typical, that's a much better word, number of siblings in your family for Americans, right? You probably find about, what, 3 would be about the middle, right? 3 kids in a family. Now, when there's 3 kids in a family, there's not an awful lot of room on the left. You can either have 2 kids in the family or it's me. But what about on the right-hand side? Couldn't you have 4 kids in the family, 10 kids in the family, 15 kids in the family? Doesn't that kind of lend itself to be a skewed to the right distribution, even although I haven't got that data in front of me? It seems very realistic that that's what would happen. Now, what's bad about skewed? Why do we even care about it? Do you know that empirical rule that we were talking about? You know, the 1 standard deviation is 68 and the 2 standard deviations is 95. There is a caveat to that rule. Only do it when the data is roughly symmetric. You're allowed a fair amount of wiggle room, but roughly symmetric. If your data is skewed to the right or skewed to the left, or just random digits, don't use the empirical rule because it doesn't give you accurate results. It doesn't really predict how many people will be within 1 standard deviation. It could be 68, but it's more likely to be 2 or 92. Now you might think, no way could that be 2. Here's a distribution for you. Right in the middle is the mean, right? If I did 1 standard deviation either side, do you see it's almost nobody? Can you see why you need a hill as well as being symmetric? Right? It's sometimes called the bell-shaped curve, right? It starts at a hill and it goes down evenly. If that's the shape, then you can do the 1 standard deviation and it's useful. Well, to finish, I'll use it to do a prediction then. Let's suppose that I know that there's a test. And the only thing I've been given about the test is that the average score was 70 and that the standard deviation was 5. But I was told that it was symmetric. I can tell you right now that if you take the mean and you add 1 standard deviation and subtract it, you're getting what, 70, give or take 5. You've got a score in the 65-75 range, and according to the empirical rule, 68% of the data is in that range. So if somebody then says, oh, by the way, do you know that this was a big lecture theatre class? And you go to universities, especially if you're doing introductory classes, as well, my experience is, I was in classes with 150 people in them. It was a big auditorium. So in this world, let's say there was 120 people. Well, if you find 68% of 120 people, I can now make a prediction, which I'm about to do on my calculator. That about 81 or 82, because it doesn't round off quite perfectly. The 81 or 82 people got a score between 65 and 75 in the test. So with very few pieces of data, tell me the mean, tell me the standard deviation, and tell me how many people are in the class and that it's symmetric. Once I know that, I can start telling you all sorts of things. I can tell you what, range, how many people got between 65 and 75. I could even tell you how many got between 60 and 80. 108, by the way, 90%, right, 95%, so a little bit more than that. So kind of powerful. If you collect all the weights of babies, and you know that this number here is 7, which probably isn't, and that the standard deviation is 1, do you see that you can now make predictions that between here and here, 95% of all babies, that's what their weight will be? And I think that's kind of a cool thing to be able to do. And large-scale studies with thousands upon thousands of people convert all that information into just a few numbers. And I've noticed the time, I've overshot it. Well, thank you for dropping in. I'm hoping to goodness that, oh, come on. Oh, good, I did record it.